Nir Lazarovich from the Technion to talk about testability of tessellated surfaces.
Okay, thank you, Arya, and thanks for the organizers for the invitation to speak here. Yeah, I must say that the last result I had on stability is like 5-year-old, I think. so I had to come up with something new for you guys. So that's this why I remember that Irit asked me a few months ago a question very much related to stability. We started working on this, and Arya and Eyal, so Arya and Eyal Itmin, who is a student, joined this effort. And what I hope to do is describe a very combinatorial problem, okay? And then what we'll do is we'll start investigating this, and we'll see that to solve this combinatorial problem, we'll actually go into groups, and then into geometry, and into topology, and some maybe linear algebra, and then back to this combinatorial problem, okay? So that's the big plan. And then the goal is on the way, know some, like, introduce some related problems of stability. Okay, so here's the problem. So let me first give a rough outline of the problem before actually defining the way that computer scientists maybe do this. So here's the rough problem. You are given a complex, a two-dimensional complex. Okay. And what you know about this complex is that for most, or maybe let's fix some constant k, and let's assume that it's at least 7. Okay? 7. So you're given such a complex, and what you're told about this complex is that for most of the vertices of the complex, okay, so I shouldn't say for all, so for most vertices V vertices of X, the link V in X, meaning the kind of combinatorial structure that the vertex sees around it, is the K cycle. Okay, so for most points, what I see around them in this two-dimensional, say, simplicial. Okay, so around most points, what I see is some kind of a K cycle here. K7, maybe, yeah, hopefully. Okay, so this is what we see around most points. And the question is, in the flavor of stability, is this complex close to another complex in which we see this thing at every vertex? Okay? So is X close to some complex, maybe Y, such that for all vertices of Y, the link is a cycle.
For my ignorance, but assume you know this for every, then this is a tessellation of the surface.
Right, so, yeah, so exactly. So the point is, this condition, what does it tell us? It tells us that locally, around each vertex, what I see is this cycle. So globally, what I see is a surface maybe disconnected, but a surface tessellated by triangles. Okay, so maybe let's record this. So Y is a surface tessellated by triangles such that around each vertex I see K triangles. Okay, so for specific tessellation. Okay, so we see how topology will come into the play here. I mean, eventually what we want to get is surfaces.
Do you have a degree bound?
Yeah, okay, good. So now we need to make it a bit more precise. Thank you. Okay, so first I should say maybe what do I mean by complexes? Okay, let's say simplicial, and it should be more general than simplicial, but let's think simplicial, okay? And I will not say more about this. And now we want to say more about what do I mean by for most. So so here one needs to count in a certain way, and maybe the best way is actually to give some kind of a degree bound on the vertices to make it into those who know what local testability is. So this is supposed to be like the sparse local testability model. So assume, yeah, so K is given, and maybe some, I don't know, bound M is given. Okay, so K is D7, M whatever. Okay, and what we're asking is, for every epsilon, we want there to exist a delta, such that if X is, again, a 2D thing simplicial complex, such that the degree of each vertex is bounded by M, and here you can take it to mean the number of edges, or maybe you want to count the number of edges and simplices around V, whatever. M is some big number that's heading in the background. Then, and you assume that for that the number of vertices, so V such that the link cycle, this or the total number of vertices is less than, oops, it should be delta. Okay, so for a small percentage, I do not see a cycle. Okay, this is what it means for most vertices, I see a cycle. And now what do we want? We want there exists Y. Okay, again, two-dimensional simplicial complex. Such that everywhere we see this, I'm writing it again, sorry. But now what does it mean to be close to X? So here maybe we want to think of two subcomplexes. Okay? So there exists maybe X prime and Y prime in X and Y, such that X prime and Y prime are isomorphic, these complexes. Okay, and the difference, okay, is small. So X minus X prime, count how many simplices in odd dimensions maybe, is a small percentage of X, and the same for Y. Okay? Is the problem clear? Right? I mean, I'm giving something that almost looks like a tessellated surface, and I want to say, okay, if I change some small things, so I'm keeping X prime, but I'm changing outside of X prime, and what I want to get is a new complex in which I actually see a tessellated surface.
So when you do X minus X prime, you talk about vertices or what?
Because the degree is bounded, where is it? Degree is bounded, it doesn't really matter. So counting vertices or counting how many simplices.
Okay. Why there exists K greater than 7?
There exists where?
K greater than.
Oh, yeah.
No, the K.
The K.
There exists K.
I'm fixing, so fix. These are kind of fixed for the problem. So yeah, good. That's a good point. I'm fixing K. Let's say K is 7. Throughout the talk, K is 7.
So for every K, there exists M. For every K greater than 7,
it's for every K and M. I want to solve this kind of problem. I mean, I didn't tell you that it's true, so. But yeah, but the result. Okay, so let's.
And just quick. So 7 is like to have hyperbolic curve.
Yeah, that's true.
Okay.
Yeah. To make the surfaces interesting. What?
Is it true for 6?
It is. Yeah, it should be. Yeah, it should be true for 6. So let's dig a little bit deeper into this problem and see how one approaches this. Before I should say, so I was about to write the theorem. So the theorem is that the answer is yes, but But the thing is, it's very much work in progress, which I should have said at the beginning. So, okay. So, I believe it's true. Is this recorded?
So the epsilon and delta depend on K and M.
The
The
epsilon
epsilon delta dependence. So
the
delta
epsilon
depends on
delta
epsilon.
dependence, yeah, for me it depends on, yeah, I'm not going to say anything about the dependence between them, but you can make those things quantitative. Okay, so yeah, so what's the approach? So we start with a combinatorial form.
The problem here is that the link might not be like a disk, but something that has or
Yeah, it could
like
be.
if you were guaranteed that all of them are disks, but just maybe degree greater than k, this would be clear, or
Not a priori, right? I mean, also this problem is, yeah, I mean, what Alon is asking is that if here, instead of just asking this is not CK, you just ask for it to be, you do ask them to be cycles, but of different K. Yeah, just different sizes. It's still not clear, right? But here we don't really care about it. The other links could be whatever. Okay, so as I promised, we start with a combinatorial problem. Okay, or even I don't know, something related to computer science in some way. And the first goal is to make it into a group theoretic problem, and really about flexible stability of a certain group. So let's do that. So here's the idea. So from combinatorics to group theory. So I'm given this complex. What I tell my students is you should draw big, right? So this is one simplex in my. Okay, let me draw another one. Yeah, so what do? We take those simplices and the first thing we do is we cut them, we do the bicentric subdivision. Okay, so we do it for all of them. And what we get here is a triangle, okay? And if we are in this ideal world where all of the links are cycles, we can think of all of those triangles being congruent to one another. And then this tells us what the angles should be. Okay, so the angle here is pi over 2. This is pi over 3, pi over 2, and pi over k. Right? Ideally, if this had k simplices around it. Okay, and this is naturally a triangle that exists in the hyperbolic plane. Right? And this should again not be a surprise because at the end we get some surface which is tessellated by those triangles, which is related to the tessellation of the hyperbolic plane by simplices. It's supposed to be the same size, okay? And the group that preserves this tessellation is the group that preserves also this barycentric subdivision and acts simply transitively on the barycentric subdivision. Okay, so this is where this comes from, and what is this group? So the group, let me call it T, the group that preserves, say, the automorphisms of this tessellation. So what is this group? This is a reflection group, right? A triangle reflection group, and it's given by the following presentation. I want more space. Let me write it here. So it's given by 3 reflections along the sides of this triangle. Here. So those are reflections. So each one of them has order 2, and to capture this angle condition, this gives us a condition about the order of AB, which is the rotation around this. So AB, so for me this is going to be A, B, C, maybe. So AB squared is 1. AB squared is 1, BC cubed is 1, and CA power K. Okay, this is the reflection or triangle. You should write 2, 3K. Shoot, I'm used to Hebrew. So the 2, 3K triangle reflection group. Okay, so that's the group of automorphism of this tessellation, the isometry group of the plane that preserves this tessellation. Okay, so this is somehow hiding in the background, but what we're given is not this ideal thing. So instead what we're given is an almost action of this group. Okay, so let's describe this almost action. And really what I'm thinking of is that this group acts on the lethal triangles, okay, in this barycentric subdivision. And the way it does so is the following. So let's say B, I have 3 colors. Let's see. So let's say B is red. So it will take this to its neighbor and back. Okay. And the same here. This is also a B edge.
So you fix one point and then
I'm really thinking of the action on the triangles, but you can think of taking a point and following it. Okay. Good.
I think he mentioned barycentric. Barycentric is fixed. No.
No, I'm talking about the cells of the 2 cells of the barycentric subdivision. Yeah. This group almost acts on them. Okay, as we will see. Again, in an ideal world, like Y, it would actually act on them. But what we're given is an almost action. Okay, so let's do C. So C is these guys. Again, they act by reflection. It's fine. Okay, and finally we have A. Okay, so A is going to be these edges. And here's where this ideal picture becomes a bit worse, because we do not actually know that around this edge there are 2 cells, right? There could have been 3 cells. Okay? But, I mean, that's fine. We're not actually looking for an action of T, but an almost action. So let's just do whatever is possible here. So, meaning, if you look at the cells, maybe I should draw the one at the back. Yeah, something like that. Okay, so you see there are 3 little triangles around this edge. Yes? So what I'll choose for A is A will just be a permutation that permutes all 3 of them. In this example, when there are 3. Okay, and the same here. And same for all.
You choose an arbitrary
Arbitrary.
numbering and just
Exactly. Yes.
some full cycle on them.
Yes. What we do know is that in most places, so for most, around most vertices or around most of those cells, what I'll see is only two of them. It will actually look like an action. Okay, so that's the observation.
Right, so is this picture happening in the universal cover? Or
This happens this is in X.
in X. Okay.
Yeah, it's just a very close-up picture of X. So let's see what happens in an ideal situation where the vertex is already right degree. Okay, so I see 7 of them. They are subdivided, and what I'm going to draw is the what do I want to do? Yellow and purple. So I see yellow between those two. Okay, and then purple between those two, and yellow and so on. Okay, and this will complete a K cycle, which is exactly this relation at C and A. When I follow C, which one is C? C is yellow. C and A, and I do it K times, I go back to this. Okay, so for most of the triangles, what I'll see is that these relations are actually satisfied.
Can I ask you a question? So in the universal cover, you basically have one axis, and then you reflect at this axis. But now you reflect basically at every axis, so it's really compatible.
So okay, so the thing to keep in mind is that there is the left action, there's the right action. So really, what I'm describing is the right action.
Okay.
So I'm kind of drawing the Schreier graph, if you want, right? So it's not what we're used to when we're thinking of it. Good. So yeah, so the upshot of this is that if I'm given a test for my problem, so such a complex X, where most of the links are good, then what I get, so from X, what I get is we call it delta morphism, right? Of T, okay? Or delta almost action, maybe. Which means that for almost all of the little triangles in my action here, the relations are satisfied. Okay. Good. So this is really the setup of stability, and what we want is to correct it to something that actually has an action, right? Which is what flexible stability and flexible stability is about. But what I want us to note is that the group T has actually more actions than what we can see coming from such complexes. And why is that? So for instance, what could happen here is that, say, this point could potentially be a fixed point for A. Okay? But in anything that comes from a geometric picture, okay, with a barycentric subdivision, it has to send this triangle to the neighboring triangle. It cannot be a fixed point.
Of the group.
What, sorry?
Of the group, no? You said fixed point of A.
This is not A. What's the name of this guy? C. Yeah, sorry. Okay, so really the kind of objects Y corresponds to is, I'm going to say, not delta morphism, actual morphisms. Okay? So actions of T, but with more constraints on them. Okay, what are the more constraints? Such that, so I want the elements A, B, and C to not have any fixed points. But that's not the end of the story, right? I mean, I could also, you can imagine A, B having a fixed point. Okay. So instead of sending A, B, instead of sending this guy to here, it might send it back there. That's bad for us. Okay, so that's those things. So and we also want it for AB. What else? BC, BC squared, BC, those guys. BC, BCB.
Just talking about all the torsion elements of the triangle, right?
Exactly. Good. Okay, so what I'm listing here is exactly all the torsion elements, all the conjugacy representatives of torsion elements of T.
So now you're really just seeing this as an action, like a permutation action of the sets.
Yes.
Okay. You forgot the like geometric structure.
Yeah, we left combinatorics. Now we're in group theory, right? But we still need to remember something. So really, what we want is that this action, the torsion elements. So those are the torsion elements of T up to conjugation. Okay, this is the list of all of them. Act without fixed points. Okay, so again, in terms of stability, what we want is not just an action of T, but an action of T with more constraints on it. Okay, but we're also given, okay, an almost action where all of those constraints are almost satisfied. Okay, so let me write this notion of stability that's behind this problem. So let me call it stability of relations and non-relations. Okay, so I'm given a generating set. So here it will be ABC generators. And I'm given relators. But I'm also given non-relators, so non-trivial elements in A group. Say A, B, etc. This list of elements. And here's the kind of stability that we're looking for. So, yeah, for every epsilon there exists delta, right? Such that if I'm given an almost action, say to S, so what is an almost action? So I'm sending the generator somewhere. I want the relations to be satisfied, almost. Okay, but here's the new thing. I want the non-relators, so this is in the relators. And I want the non-relators, G, to be very not satisfied. Okay, so for this means that the number of fixed points is very small, right? So for any G in the non-relators, this list. Okay, and really what you should be thinking here is conjugacy classes of elements and not elements. Think about it. And what you want, so then there exists an actual action, prime, from this free group to Sm. Maybe I'm really thinking of flexible stability, so I'm allowed to add here a little bit. What's the epsilon n? Okay, such that now these are really satisfied. Let me write it in norm. And these are really not satisfied. Okay, whenever I write norm, I mean the normalized Hamming distances. I will now.
What is there in the index?
Sorry?
What is there in the index of the symmetrical?
Sn plus minus epsilon n. So I'm allowed to change. This is flexible stability and stability. Again, also in the problem, you see that I'm allowed to change the size of x prime and x. In fact, let me point this out. This problem is not true if you do not allow to increase the size. Okay? So the kind of strict stability in some scenarios is not possible just by Euler characteristic computation kind of thing. So really, you do have to think about flexible stability for this.
So this is
But do you know that the 237 is not flexible stable?
Okay, so that's maybe the first question to ask is, I mean, here we're asking for maybe more.
That it's not stable, but flexible. I guess.
No, I'm not claiming that. I'm not claiming that. I'm saying that this, this particular thing where we ask for certain relations and non-relations in this case.
Is flexible stable.
Is flexible stable, but will not be stable. Or in other words, let me just convince you why this is true. If you know that the link at any vertex is a cycle ck, okay, then you can, and let's say k is 7, okay, then you can show that the contribution of this vertex to the total Euler characteristic is minus 6. Okay, so if the number of vertices is just not divisible by whatever 6, it's not going to be an integer number. So it cannot be the Euler characteristic of a surface.
But if, so the points are not really equivalent, namely, you are not claiming, but these are.
They are equivalent because here I'm allowed to change the sizes of x and y, right? So it is the flexible kind of stability.
Okay, let me ask you to get it a simple way. Forget about this problem.
Yeah.
Now, the 237, you are about to prove that it's a flexible, stable group. Can you prove that it is not stable?
No, I cannot, I don't know how to prove.
So the argument you just gave me here does not apply for the group. Because for this...
So again, so it applies to stability of relations and non-relations.
Can I just...
It's a different problem than just stability. So really what I'm going to prove is that 237, this group is not only, well, okay, we'll follow that it's actually it is stable, but flexibly stable, sorry. But what we'll prove is that it's flexibly stable with relations and with these relations and non-relations.
It gives a flavor of a residual finiteness where you can separate.
Yeah, I mean we'll see. Yeah,
Just a comment. This is exactly what we called weak stability.
So it's not okay. Good. So it's not what you call weak stability.
So you are showing that it is flexibly weakly stable, but not flexibly, but not weakly stable, but weakly for a certain. Yeah.
I got a headache. You guys had more caffeine than I did. It's not exactly weak stability, because for weak stability you really want to take all elements. And here I'm telling you which are the elements that I want to act without fixed points. Okay. Let me move. Oh, sorry. Okay.
You don't take all non-relations? You don't take all non-relations?
No, just the torsion
Only
elements.
torsion elements.
Yes.
Okay,
Yeah.
thank you.
Okay, good.
I want to say that rho prime is close to rho, right?
And rho prime is close to rho. Does this make sense? Let's pretend it does. Okay, good. And this, okay, I should say that at this point, what really is hiding here is this triangle group, and we know that surface groups are flexibly stable. This is something I did with Arya and Yair Minsky. But we do not know that stability is something that passes from finite index. This does have a finite index surface subgroup, but okay. But also the problem is a bit different, right? Because we're looking for other properties. Okay, but the idea should somehow be the same. I mean, the same kind of technique of showing stability of surface group should kind of work here. But one has to be a bit careful. Okay, so let's maybe say what we do here. So let me rewrite this presentation of T. Okay, so I'm going to write it with 5 elements, the same kind of relations. Okay, AB squared, BC cubed, CD, K. Don't want the last one, I do probably. Maybe I don't need the last one. T conjugates A to D, okay, and T. Okay, why am I writing this in this one? So really what I'm doing here is I'm thinking of this triangle, okay, I'm thinking of this as an orbifold. This is pi over 3, this pi over k. And what I'm doing is I'm taking out one point from this triangle. Okay, when I do that, what I get is this, I mean, you can think of it as it retracts to to the one skeleton of this triangle, and this is a graph of groups. Okay, and this is exactly this graph of groups. Okay, so let me maybe write it like that. Let me call this guy T0. Okay, so T0 is supposed to be the fundamental group of this orbifold when I take out this point. Okay, that's great. So T0 is a virtually free group. And with Are, we showed that virtually free groups are stable. So what it means is that I can take this almost action that I'm given, rho, and at least correct all of those relations. Okay, leaving out T, the new guy. And get something that's actually an action. This action, I'm not claiming that it will satisfy this, but still the percentage of, I mean, these will still hold for this new action. So again, let me say that T0 is this, the pi1 of this orbifold with 1 point removed. So any action of T0, which is what we get after we apply our theorem, gives us a cover of this guy. So orbifold cover. Okay, so let's maybe give it a name. And say this is S0, and the cover will be S hat 0. Okay?
Say orbifold, you mean you remove this point from each one of the triangles? Like what exactly is this picture? I'm sorry.
So this is this is the pi1 of this orbifold.
It's not just the circle.
It is just a circle, okay? But I want to think of the triangle minus a point because I'm going to fill back the point into this picture later. Okay, so any action of T0 corresponds to a cover. Okay, so here I get this cover of this guy.
I think Alon is asking, it's an orbifold in the sense that when you do pi1, you don't treat it topologically as that picture. You think of those
No, you
vertices.
need to remember that there are
the
groups on the edges and the...
Yeah, okay.
Yeah, so again, this pi1 is exactly this T0 that's written there. So
Action on what? The action of this T0 on what?
The action of T0, so this is this fixed homomorphism on one up to n.
Okay.
Corresponds to a degree n cover of S0. So here it is. I'm not really going to draw something. Okay, but what you should be thinking of is that for most of the places, since T is satisfied almost everywhere, I will lift this triangle to a nice triangle with a hole here. And in some places, this will open up. This triangle will open up. And we'll have an angle of more than 2 pi, a multiple of 2 pi, around this missing point. Okay? And what we're going to do now is just fill in this point. I can get a branch covering instead of a branch covering. So maybe this is like this. It covers S. So this is fill in the point, the missing points. Okay, and what I get here is this is not a covering map, this is a branch covering. And really what it means is almost everywhere it looks like a covering map, except for those points in which I might see an angle of, say, 4 pi or 6 pi or something like that, covering a 2 pi angle. Okay, like the map z goes to z to the k. Good. Yes. So we went to group theory. I didn't say this is maybe starting to see geometry. Okay. And here is how we use this. Right. So eventually, what we want to get is an honest action, not an almost action, meaning a covering map and not a branch covering map in this language. And the way to do it is, what we'll do is we'll take this surface S bar and we'll chop it up into pieces, such that in each piece, what we see is something that looks like a part of a covering. Okay? Well, now we do have those branch points, so really the goal is to, so here's the proposition. And this is really the technique that we did in the paper with Yair and Alia. So there exists a graph, gamma, inside S bar. Okay, so this is an embedded graph. Such that, so first of all, the vertices of gamma are the all those problematic branch points. But really, I also want to get rid of any kind of torsion that's left there. Okay, so I'm going to include those as well. So cone points. Okay. Edges of gamma are going to be geodesics. And are going to include all of the mirrors of this orbifold. If this means anything to you. Yeah, note that S bar is not yet a surface, it's an orbifold. Yeah, eventually we want to get something that is a surface. Okay. And what else? We want to get to a situation where between any consecutive edges of gamma, so the angle between consecutive edges is less than phi. And finally, the total length of gamma is divided by n. The degree of the covering goes to 0. It goes to 0, meaning as what's the parameter? Delta. Okay, let me do a sketch. So here is my branch covering. This guy. And in here I have points that branch over this little guy. Okay, so the angle here say is 6 pi instead of 2 pi. Stuff like this. And what I want from my graph is that it will connect somehow those points and break them so that the angle here is less or equal than pi. Okay, so maybe I should add another one. Okay, this. Imagine a surface. So on. Okay, so this is my graph gamma. Embedded graph on my orbifold. It connects all of those branching points and also connects all of the cone points. I know how to draw them. now what happens is, if I look at S bar minus gamma, okay, then what I get is really a surface because I cut out all the cone points. They're not there anymore, right? They're included in gamma, so I threw them away. I don't see any branch points because I cut them as well. And the angle between any two things is less or equal than pi. So really what I'm seeing is, so this guy is a surface, so a compact surface with, I'm going to write locally convex boundary. That covers, or that has a map to S. Okay, so you should imagine taking this, cutting along those graphs, okay, this graph. And what we are left with here is something that really looks like a surface, and the angles here are less or equal than pi. So this means that its boundary is locally convex. Okay.
In the simplicial case, gamma is part of like your simplicial graph?
Sorry?
Gamma is constructed using edges of your simplicial complex?
No, it's not. It's a good question. It's not. It's just really a geodesic. I'm really thinking geometry. At some point, I should have written group theory to geometry. That's before this. Yeah, but they're kind of, I mean, they're crossing somehow the edges of the simplicial structure. That's true. Okay, and now for these guys, what we know is that they do belong to some cover. Right, so this follows from the fact that they have a like general cat zero kind of geometry arguments. Tells you that S bar minus gamma is contained in some cover. Which kind of symbol did I not use? Or maybe S still? Fine. Okay. This just means that, basically means that S bar minus, okay, it's a bit more than that, but S bar minus gamma, the fundamental group of S bar minus gamma is actually a subgroup of S. This is kind of what's hiding behind this. And this, I'm not saying anything about what's the degree of this cover. Right? It's just in some cover, possibly infinite degree. Okay, so really I cut this graph, I get, let me do the sketch. So I cut my graph somehow. Here I get just the surface, I don't see any cone points, I don't see any branch points, and here's my locally convex boundary. And what this says is that it belongs to some infinite cover. Okay. Should I finish 10 before, or maybe let me use Gunar's excuse. Since I did start on time, I should get extra. No. So when should I finish?
Maybe 5 minutes and then some time for questions.
Okay. Let's see what we can say in 5 minutes. What do we want? What we actually want here is to say this is not just contained in some possibly infinite cover. We want to say it's contained in a finite cover. That's kind of the surface that we were looking for, the Y that we were looking for all along, in such a way that the difference in area between the cover and this guy goes to 0 as delta goes to 0. Right? This will mean that X and Y are close. Okay, so really the problem now is what we want is find efficient S tilts. S tilt, meaning, so what is efficient? Efficient means that the difference, like that, area over M goes to 0 as delta goes to 0. And this is really a kind of geometric group theory kind of question. You're given a finite, you're given a finitely generated subgroup, like the fundamental group of this guy, and you want to find a finite index subgroup, okay, that contains it and does not contain certain elements. This is exactly the kind of separability always studied in geometric group theory. But note that we want more here. We want this guy to be a surface and not an orbifold. Okay, so that's means that we have to be a bit more careful. Yeah. So here, really what we do is the following two statements. So we want to find efficient S tilde, and here are the two statements that we want to show. So one. First of all, there exists a finite cover. I'm not saying efficient, but at least it should be finite, not infinite, right? So finite cover S bar S that contains S tilde over S that contains S bar minus gamma. Okay, so finite. So this is one. And two is there exists I want to say that S, that there exists some, S, I'm running out of
Bow tie.
decorations. What?
That's a good one. Bow tie is a good next one.
I don't know what it is. This?
Yeah, there you go.
So fancy S like this. That is still compact surface with locally convex boundary. Okay, it will satisfy this. It will be efficient. Compact with locally convex boundary, such that the area of so the area of this will be small. Okay, such that this, so far I could just take S bar minus gamma. So the extra assumption is that I want all boundary components. Sorry? Of this guy to be bounded in size. Bounded in. Okay, so again, there are kind of two problems. One is just find any kind of closed finite cover that will contain S bar minus gamma. Maybe not efficient. Find any. And the other is find something that's not closed. It has boundary, but all of the boundary components are bounded in size. And the point is that if you manage to do those two things, and here I should say this should be a surface. Right? It's the kind of thing that we want. In case I didn't say it here, this should be a surface. Okay, and kind of little piece of I call it linear algebra, but really it's just souped up pigeonhole principle. Tells you that in fact you can do it efficiently. Okay, so there exists S bar as we wanted, such that the area of S tilde minus S bar minus gamma goes to 0. Okay, so somehow combine the two, and the idea is not that difficult. I mean, you think of you have your surface with short boundary components, right? And what So this is what 2 gives you. I've been able to embed my S bar minus gamma into something slightly bigger with bounded boundary components, bounded length boundary components. And what 1 gives you is that you can always close it, maybe inefficiently, but since they are bounded, they come in very specific types. Right? So you can just count how many of each type do you have and make it into a problem about multisets and play with that. Let me just state a very stupid lemma that's used there, which is kind of fun. So if H is a subgroup of Z to the N, okay, and you take H and you intersect it with the non-negative Z to the N's, then this is a finitely generated semigroup as a semigroup. Okay? And this is exactly the kind of thing you want here. So the N records what kind of types of boundaries you have. So really Z to this guy is the multiset of counting how many types you have. And this H measures which one you can fill or which one exists.
And H is also finitely generated. H is finitely
H, yeah, H is obviously finitely generated. It's a subgroup of Z to the N. But really the point here is that when you intersect it with some nice cone, you will get something that is finitely generated as a semigroup. So, yeah. If you want to ask me afterwards how this is used in this, feel free to do so. Thank you very much. Sorry for going out of time. Yeah, sorry.
So in the combinatorial thing, when you're sort of changing the number of degrees, you're taking x prime is a subset of x, so the n gets smaller. But in the flexible stability, you're sort of allowed to make the n get bigger. So why is that okay?
Oh, I see. Yeah, I mean, here, what you see at the end is that you can, I mean, okay, let's say you can always make it bigger. Just take whatever example you have of, a surface tessellated, some small thing, and repeat it until it's bigger than n, right? I mean, that should never be the problem. Is making it bigger than n. It's bounding how much bigger you need to make it. Yes.
Item 1, that's Scott's theorem, right?
Sorry?
Item 1 is Scott's theorem, right?
Is what theorem?
Scott's theorem.
Scott's, okay, good. It's not. It's kind of Scott's theorem. It's kind of Scott's theorem. But really what you want to say here is that any torsion-free subgroup is contained in a finite index torsion-free subgroup. That's slightly different. That's slightly different and requires some proof. And actually, an interesting question is whether this is true in linear groups. I don't know. That any torsion-free subgroup, like finely generated torsion-free subgroup, is contained in a finite index.
I mean, that's
something like that.
That's almost clear, right?
I don't know. I mean, here the proof we give is completely topological. I mean, it just uses the fact that orbifolds are residually torsion-free and.
Sure. Yeah. So you need to combine.
Yeah.
I mean,
yeah. But I can tell you afterwards. I mean, maybe what's the. Yes.
So you said that restriction on k, it gives you curvature, right? Negative curvature.
Yes.
So, but if you take 6, this little thing locally convex will be still true.
You mean this cutting technique?
Yeah.
Is that maybe I should ask Aria? Is that where it fails? I mean, thinking of that. Yeah, I mean, I believe that the k equals 6 should be true because we know that virtually abelian groups are flexible. Okay, slightly different notion, but still.
I also believe, but Is it true by this proof? I don't
We
know.
do not know. That's
Okay.
yeah. Proving it
but
for z squared.
But in your argument, local convexity, you require this negative curvature. Yeah.
Yeah, this. We definitely use negative curvature there to relate somehow the fact that area grows exponentially with respect to lattice is something that we use, but maybe we don't. Maybe it's enough way to grow quadratically. Anyway, we can discuss it.
Mm-hmm. Okay.
So we are a bit over time, so maybe we can continue discussing during the session. Let's thank Nir again.